All right, so moving on to Chapter 3. And Chapter 3 is a pretty short chapter. We're just going to look at a few different topics. In fact, Chapter 3 is really similar to Chapter 2, and it just sort of dovetails into it. We want to define a few things about electricity, current and resistant. Current is the rate at which charge flows past a point. Remember, charge is our Q, at which charge flows past a point in a given time. All right, so charge, our current, then is defined as Q divided by time. So the basic SI units for this are the coulomb per second. All right, so 1 coulomb of charge in 1 second is the SI unit for current. But the unit that we use for this, which is equal to 1 coulomb per second, is an ampere. You can see it as an ampere. I think there's an accent here. Or more commonly, just as amp, or as we'll do it, capital A. Now, the conventional direction of current is the direction that protons would flow in a circuit, or positive charges. The reason for this goes back to Benjamin Franklin, who did a lot of the foundational work in electricity and how we use it today. He thought that protons flowed and not electrons. And so when he developed sort of how we see circuits today, he developed it with the idea that protons are moving through the wire, not electrons. So whenever we talk about charges, our current flowing, we're going to imagine that instead of them being electrons, as we know what they are, that they're actually protons. So a proton would come off of this positive side of the battery and would move in that direction. Remember, protons move from high to low potential. So a proton would move from high in this direction to low potential, high to low potential. So that's the conventional direction. Let me just write that. Protons move from high to low potential. If you remember back from Chapter 2. Now, if we are looking at electrons, the actual flow of current, sorry about that, the actual flow of current, which is the flow of electrons, would actually be in this direction. But whenever we talk about the flow of current, we talk about the flow of protons or positive particles. All right. Positive charges move away from the positive terminal. Remember, that is the high potential side, and towards the negative terminal. Remember, that's the low potential. Let's go and look at measurements of current and voltage. In a circuit, and if you're in a lab, you've used these. A circuit, one uses an ammeter to measure the current. The ammeter is always hooked up in series with the circuit. So whenever you hook up an ammeter, you have this circuit. The current is going in this direction, and I would take the ammeter and put it right in line with the wire on the wire in the circuit. So you always hook up an ammeter in series. Now, whenever you're making a measurement, in general, when you're making a physical measurement, you want the device to change the system as little as possible. Ideally, it's not going to change it at all, okay? But when you're measuring things in an electrical circuit, you have to be careful, because by actually putting in the device, you can change what the circuit does. And so your measurement then would be incorrect. So think about this. Is the resistance of the ammeter big or small? If I put in a big resistor, is that going to change the circuit? Or if I put in a small resistor, is that going to change the circuit? Now, we haven't really talked about resistors yet, but let me just sort of give you a general idea. A resistor is something that resists the flow of electricity. So something with a lot of resistance will heavily resist the flow of electricity. So that if the resistance keeps going higher and higher and higher, then you'll get no flow of electricity at all. Whereas if the resistance is very, very low, then it's not going to impede the flow of electricity at all. So should the ammeter have a large or a small resistance? Well, as you probably know, the ammeter should have a small resistance. And in this way, this doesn't impact the circuit at all. Okay, so an ammeter has a very small resistance. It does not resist the flow of electricity hardly at all. So in that way, it doesn't impact the circuit when you place the ammeter in series with the resistor. So to measure the voltage in a circuit, use something called a voltmeter. As I said, you have a whole lab experiment just on ammeters and voltmeters. The voltmeter is going to be hooked up in parallel. Because you remember that devices in parallel, they have the same voltage. So if I have a voltmeter here that I've hooked up in parallel, whatever the voltage is across this resistor, I will also have that voltage across the voltmeter. All right? So that's why you hook it up in parallel. Now, which would you want to have the voltmeter? Do you want it to have a big or a small resistance? Remember, a big resistance means that hardly any electricity at all flows through it. And a very small resistance means that all the electricity will be allowed to flow through it. And in the case of a voltmeter, you know, with an ammeter, it wants to have a very small resistance. But with a voltmeter, you want a very big resistance. That means that as electricity comes up through this wire, hardly any of it is going to go through this wire because there's such a large resistance with that voltmeter that hardly no electricity goes through that wire, just enough to register on the voltmeter. So almost all the electricity goes through the resistor, which is what you want. You want the circuit to go on as if the voltmeter isn't even there. You want the voltmeter to impact the circuit as little as possible. So there is a very tiny amount of current that runs through the voltmeter, but just enough to register on the needle. All right, so in the lab, you learn what that is. It's on the order of milliamps. All right, you can try this quick test or just about voltmeters and ammeters. I think there's a second one down here. And then we'll pick up with Ohm's law next.